Hello friends, welcome to our channel. In this video, we are going to look at problem 802, Find Eventual Safe State. In this video, our motivation is to solve it using vanilla breadth-first traversal or depth-first traversal. Here we are given a directed graph of n nodes, and the edge relations are given by a 2D integer array called graph. So the graph I is a array, which means node I has edges connecting to this nodes in the graph I. So here, the second paragraph is very crucial. So a node is a terminal node if there are no outgoing edges. In other words, the out degree is 0. And a node is a safe node if every possible path starting from that node leads to a terminal node or another safe node. So this is actually a very important definition, right? So here it means every possible path, right? So we want to return an array containing all the safe nodes of the graph. The answer shall be sorted in ascending order. So here in this video, we are trying to code and use and digest the logic. We're not going to pursue the most deep logic. So here are several examples. So in example 1, so the output is 2, 4, 5, 6. Actually, you can see 5 and 6 are terminals because their out degrees are 0. So similarly, you can look at example 2. We're not going to go into details here. So the constraints basically give some consistency assumption and the problem size. For example, the number of nodes is bounded above by 10 to the power 4. And graph I is sorted in a strictly increasing order. I will say in the code we are going to share, we are not using this in a very good fashion. But here we are mainly focusing on understanding the logic, especially understanding this safe node definition. So because it affects how we do the coding. With that said, let's look at the coding. So let me first add some annotations here. What I'm going to use is nothing but vanilla BFS or DFS. So notice that for BFS, if I want to write in an iterative format, it involves some queue data structure. For DFS, it's going to involve some stack data structure. This you are going to see. So with that said, also because of this definition, safe node, we are going to use the inverse graph. Basically, we inverse the directions of the edges. Because in this problem, by definition, the graph involved is a directed graph. So first, I'm going to get the number of nodes, right? So this is the graph. So here, this graph is in a list of list representation. So I'm going to use the dictionary with the container set. So this is good for retrieval, right? So here I'm going to do this. So set for I in range n, right? So similarly, I can do for this, I'm going to use a capital G. So this basically gives us, this G is the original graph. So basically, it's a node and the neighbors dictionary. The neighbors are in the format of set. So this is a reverse graph or inverse graph. So now we are going to iterate over this graph to get this two pieces of information in good format. So for I neighbors in enumerate graph, because here we are going to retrieve the name of the node, so we using enumerate function. So out degree. So we also need to get the out degrees so that we can know the terminal node. So let me do this. Out degree. So I'm going to use collections default dict. So I'm going to use integer. In other words, map everything to be 0 at the very beginning. So we can do maybe like this. So just write like this. So the outer degree at I, because it's going to increase by 1, right? Because not by 1, by the length of neighbors. So then we're going to look at the edges for G in neighbors. So in the original graph, so it means that there's an I to G edge for G, right? So basically we're going to do G, I, add G. And in the reverse graph, so we're going to use G pointing to I. So the thought is this. So we are going to do traversal, a multi-source BFS or DFS from the terminal nodes and in a backward direction. So where we can arrive, those are the safe nodes. But of course, there are some other condition checks. So this is the building the graph. So next, I'm going to get the source first. First, I'm going to see for I in range n. These are all the nodes if outer degree of this node equals 0. So actually, you can print out the source to see what you get. For example, 1. So you get the 2 terminal nodes of 5 and 6. So now let's comment this out and continue to do the coding. So next basically is DFS. So what I'm going to do, first I'm going to get the terminal nodes. So the terminal nodes, I'm going to make it a set first. So this one, I'm going to use it to check, right? So then visited, it's a set. So those are the sets regarded as safe nodes, right? So now we're going to do the standard DFS traversal. Then we have the source, and then we pop the node. The node will be source pop, right? Then first we check if node not in visited. We haven't visited yet. So we're going to visit it, add this node. So mean this is a safe node. And then we are going to check the neighbor. For neighbor in this reverse graph. So as long as we can arrive at this, then what I'm going to do first is G neighbor. So I'm going to remove from this node. Originally, if you just start the procedure, so this node is actually a terminal node. So you can think of, if I can, from this node, I can arrive at this terminal node. I first remove this terminal node. Then this place here, then we have another check condition. So if neighbor not in visited, so this is for DFS or BFS. Of course, here I'm using pop from the right is DFS. And then the problem logic is here. For this node to be a safe node, so we want that after we eliminate this node, and then we do a set difference, so terminal nodes. So I will see if not, right? In other words, so this condition means here first we should this is for DFS we should seek not visited nodes yet, and this condition is the key for the terminal node for the safe node definition, because now originally the neighbor can arrive at the node, right? Then if this is the terminal node, think of, then if after you remove this node, it then means the neighbor of this node contains no other terminal nodes, right? Or this is the besides the terminal node is empty. It means that from the neighbor, it can only go to terminal nodes. So this is the safe. This neighbor will be a safe node. Otherwise, if this is not empty, so basically it means that they can arrive at other nodes which are not terminal nodes. So or non-safe node. So this will be not a safe node in the definition of this problem. So here I'm a little bit not clear. So let me explain again. So this means that, so after you delete the node, then this means that this neighbor cannot arrive at the other node besides the terminal nodes. So, or safe node, because if you go continue, right? So then we are going to do source append neighbor. So afterwards, you just need to return sorted visited. So this will be a complete code for this problem. Let me first do a test. Yeah, it passes the 2 test cases. Now let's look at the generic case. Right, it passes all the cases. So now what I'm going to do is to change this one a little bit, because here we append from the end and pop from the end. So we are using this source as a stack, right? So this is DFS. So for BFS, so we can do, let me copy this one and comment this out. So we can do this. So we can make it a deck, collections deck. Then here, if we pop left, so we append from the end and pop from the head. This will be a queue behavior. So this corresponds to a BFS solution. Let's test that. Yeah, it passes all the cases. Here I want to give you some further challenge. So here actually we are focusing on the definition of a node is safe, right? It basically determines how we do the coding. So this problem actually can be solved using King's algorithm for topological sorting, and also you can mix the code even better by considering this this one, this constraint. So here I didn't pursue that. So with that said, I guess that's basically about it for the current video. Thank you for watching.